All right, so far we've been talking about Bronsted acids, right, in terms and bases, which are defined in terms of donating or accepting protons. We're going to expand now to a more general definition of acidity and basicity, which is the Lewis definition. And the Lewis definition um, includes, other acids and bases that don't involve proton transfer. And so the way this is defined is a Lewis acid accepts an electron pair, and a Lewis base donates electron pair. If you have trouble remembering this, the way I remember it is acid accepts. I know that Lewis bases and acids have to do with electron pairs, not with protons. And so I just remember AA, acids accept. So yeah, since this is an inclusive definition, all Lewis acids and bases are also Bronsted acids and bases. The nice thing here is that the Lewis definitions can be used in aprotic solvents. That is, solvents that don't have protons that can move around very easily, that have that autoprotolysis. And so here are the different types of Lewis acids. You can have Lewis acids, like a very common one is Lewis acids that have an incomplete octet. So boron, will form stable but reactive compounds with 6 valence electrons. Beryllium is similar. It will form stable but reactive compounds, Lewis acidic compounds with only 4 valence electrons. So boron here has 6 valence electrons. It really wants to gain an electron pair. It wants to accept an electron pair. That's why it's a Lewis acid, and have a full octet. So here it's reacting with ammonia, which is a Lewis base. It is donating an electron pair. And so you have a Lewis acid and a Lewis base that together make this one compound. You can also have this take place with a coordinatively unsaturated metal cation. And so simple examples, just thinking like a bare metal ion, that would be a Lewis acid because it's going to accept a Lewis pair, a lone pair, sorry, and from a Lewis base like water, the lone pair is on the oxygen, and it can do that 6 times to make something that would be more stable, a cobalt hexaaqua 2+ complex. So, all sort of uncoordinated metal ions are Lewis acids in this way. And so if you dissolve, let's say, the ramifications of this are pretty big. If you dissolve, let's say, cobalt chloride, right, Cl2, just dissolving that in water will decrease your pH because of the Lewis acidity of the 2+. Another type of Lewis acids are ones that can complete their octet with some rearrangement. So carbonic acid, shown on the right here, is an example. CO2 can, carbonic acid. Yes, this is carbonic acid. Actually, this is carbonate. Okay, this is carbonate ion with an H there would be carbonic acid. This is bicarbonate ion. But CO2 here is a Lewis acid because it can react with the Lewis base, hydroxide, looking at it in terms of the lone pair, does some rearrangement, and that is a valid form of Lewis acid. And then the fourth type is a type that can form when you're expanding an octet. Here's an example where there's no protons involved at all, again. And silicon, we said from chapter 2, since it's in group, since it's in period 3, it can form an expanded octet. So here it has an octet, but it can form an expanded octet, which violates the octet rule, but that's okay for silicon because of the involvement of d orbitals. And you can see that then this would be considered a Lewis acid. It's formally, this arrow should be going to the silicon atom, but you get the idea. This is a Lewis base because it's donating electrons, and the silicon tetrafluoride is a Lewis acid because it's accepting electrons.